Welcome back everyone to part 2 of our classification code along. In part 2 we're going to create the model and then show you how to help prevent overfitting of the model. Let's head back to the notebook and continue where we left off last time. Okay, I'm going to begin by importing TensorFlow. Actually we'll say from TensorFlow.keras.models import sequential. Make sure you spell import right. Run that, and then we'll also say from TensorFlow.keras.layers import, and we'll first start off using dense layers, but we'll also add in dropout layers later on. Okay, so let's create a very simple model given what we know so far about creating models. So right now, in my training set, I have 426 rows, so not a whole lot of rows, and then 30 features. So what I will do is I will create a sequential model, and then I will add in a first layer of 30 neurons. You can say units equal to 30 if you want, and then the activation will just be a rectified linear unit. And then we will repeat that, except we'll go ahead and cut that in half. So the next layer will go down to 15, and we'll keep things simple so that we have one last output layer, and this is just going to be one neuron. However, the activation, and this is critical, will be sigmoid because this is a binary classification problem. So for a binary classification problem, we want that last activation to be sigmoid. Check out the theory lectures on this if you are a little fuzzy on why we're choosing that specific activation. So we have binary classification, one neuron, outputting something between a 0 and 1, and that will decide what class this belongs to, either malignant or benign. And then we will compile this, so we'll say model compile. And we also have to make sure this loss call is correct. This should be binary underscore cross entropy in order for it to work correctly. And then the optimizer, we have lots of different options here, but we'll go ahead and just choose an atom optimizer. So we created our model, and now it's time to train the model. We'll say model.fit, and we'll say x is equal to xtrain, y is equal to ytrain, and then epochs, and I'm going to choose a really large number of epochs here, so 600. This is probably way too many for this particular training, but I want to specifically actually show you what it looks like when you overfit to your training data. And to do that, we're also going to pass in our validation data. So we'll say validation data, and we'll pass in xtest and ytest. So go ahead and run this, and this will take a while because we're running it for so many epochs. So I'm going to fast forward in time until this is done training on the 600 epochs. So that's 600 times through the entire training set. So let me fast forward in time. Okay, this is just finished training for those 600 epochs. What we're going to do now is we'll go ahead and plot out the loss. And remember, we passed in our validation data during the training. So we'll be able to plot out both the training loss and the validation loss. Recall that I can say model.history.history, and I can pass that into a pandas data frame, and we'll call that losses. And then here's my losses. I have the training loss and the validation loss. Let's go ahead and plot this out and see what this looks like. So here are my losses, and this is a perfect example of overfitting. So what is the key characteristic here of overfitting? You'll notice in the beginning, during the first couple of epochs, both validation and training loss are both decreasing. That's good. That means we haven't yet overfit to our training data, and as we go along, we're decreasing loss in both the validation set and the training set. However, at a certain point in time, notice that our training loss here in blue is still going down. However, our validation loss is beginning to increase. That basically tells us that we're overfitting to our training data set. So we have a clear indication here that we're training just for too many epochs. Notice the validation loss gets worse and worse after these epochs. So what we're going to do is we're going to see if we can use early stopping. So we've obviously trained too much, and what we're going to do is show you how to use TensorFlow Keras callbacks to actually, based on your validation loss, stop the training before it gets out of hand as shown here. So I'm going to copy and paste our model again. And this is kind of important in order to show this because we don't want to keep training on the same model. I want to recreate the model fresh. So I will copy and paste these commands. So scroll down, go ahead and basically redefine your model again. And then let me show you how we can use callbacks. And these are not the only callbacks we'll be using throughout the course. This is our first instance of using one. We'll say from TensorFlow.keras.callbacks import, and the callback we'll be learning about right now is called early stopping. And I would encourage you to call help on early stopping to see the full details on it. But basically what's happening here is we have to choose a metric to monitor, and in our case it will be validation loss, this orange metric right here. So we're going to be tracking that validation loss, and then you can also specify things like the minimum change required. Also, there's patience, which is the number of epochs with no improvement after which training will be stopped. So it doesn't just do a hard stop the minute that validation loss goes up a little bit. You can see that throughout training there is a little bit of noise, so maybe we want to wait a couple of epochs. So we can have that patience parameter there as well. And we also have different modes of training. So lots of different things you can explore here, and you can even see the full example that's available to you in the docstring. But let me show you how to use this early stopping. And the early stopping has basically two steps. One is to define the variable early stop is equal to early stopping. So we do that actual call. And in our case, we're going to be monitoring validation loss. And then the mode that we're actually looking for is min. So there's a couple of different modes here. We can go back up here and check them out. Recall that the mode is basically, what are you actually trying to do here? Are you trying to minimize the thing you're monitoring? Are you trying to maximize the thing you're monitoring, etc.? So you can imagine if our metric was accuracy, accuracy is something you want to maximize. If our metric is loss, essentially the reverse of accuracy, loss is something you want to minimize. So keep that in mind. And there's also this nice little auto string that basically the direction is automatically inferred from the name of the monitored quantity. So it'll infer it based off the string. That usually almost always works, but just in case it doesn't, I would recommend that you manually put in min or max. It also lets you know that you know enough about the metric you're actually tracking to understand what you should be doing for early stopping. So in this case, we're tracking our validation loss, which is what we want to minimize. Because if we have a loss of 0, that means we have a perfect fit. So we'll go ahead and say early stopping, monitor our validation loss, try to minimize it, and we'll also say verbose is equal to 1, basically just have a little report back, and then we'll set patience equal to 25. That means we'll wait 25 epochs even after we've kind of detected a stopping point because of noise that could occur. So we create this early stop variable, and then upon calling model.fit, and I'm going to copy the same command we used before. So up here we have our original model fit command. Just go ahead and copy that. So we'll go ahead and copy the contents of that cell. Make sure you've redefined the model again, otherwise you'll accidentally be training the old model. So we just redefined the model again, and now I'm calling model.fit. Everything looks the same, except now I'm going to add in a couple more lines here. We'll say callback parameter, or callbacks, is equal to, and you actually pass this in as a list, even if it's just one, and you pass in that early stop callback. So go ahead and run this, and now what's going to happen is it's going to attempt to run on 600 epochs unless the early stop is triggered. And in this case, note that the early stop was triggered. And if you scroll down here, it stopped training after 81. So it has that early stopping call. So that's nice. Now we know that 600 was too much. And what's also nice about this is you can now, with early stopping, choose some arbitrarily large number of epochs and then indicate that you want it to stop early with this callback. So now you don't have to worry too much about choosing the correct number for epochs, since callbacks with early stop will take care of that for you automatically. Let's now check out that model loss. So we'll say model loss is equal to this pandas data frame call on model history.history, and then we will say model loss plot. Go ahead and run this. And this is exactly the kind of plot that we want to see, where loss and validation loss are both beginning to go down, and right as they begin to spread out, that's probably where a good indication of where we should stop training. So notice this flattening out, that's okay behavior. What we want to prevent is validation loss beginning to increase, and that's what was happening, so early stop was triggered. All right, so the third thing we can do to try to help prevent overfitting is add in dropout layers. So dropout layers will essentially turn off a percentage of neurons randomly. So let's come back up here, and I'm going to copy and paste my model again to make sure I don't accidentally keep training my old model. So there's my model again, and what I'm going to do is you can do this in the same cell or in the cell above it, we will say from TensorFlow.keras.layers import dropout. We've technically already done this, I just want to clarify that the dropout call comes from keras.layers. And you should have already imported this before, but go ahead and just do it again. And what we're going to do is after each of these two dense layers, we will add in the dropout call. We'll say model.add, and then we say dropout, and then the main parameter you choose with dropout, you can do Shift Tab here, and you'll notice that the main thing is basically rate. And the rate is the probability that you're going to randomly turn off the actual neurons. So it's the fraction of which you're randomly turning them off. So if you put a 0, that means you're taking 0% of the neurons and randomly turning them off during training. If you put a 1 here, you typically would never do that, but that basically means that 100% of the neurons are going to be turned off randomly for each batch of training. So what is a really common value is somewhere between 0.2 and 0.5, and essentially that means is half the neurons during each batch, essentially each batch is one entire epoch of training. In our case, because we haven't specified a batch size, half of those neurons in this layer of 30 are going to be turned off. So their weights and biases won't be getting updated. So we'll go ahead and put that here as well. And that means, again, about half of these neurons are going to be turned off randomly. So it's not the same neurons each time. It's a random subselection of 50% of the neurons. Okay, so that each neuron has essentially a 50% probability of being turned off during each batch. So go ahead and rerun this. So we redefine our model, and then we'll use this in combination with dropout. So we can still retain the same early stopping here, but I'm going to copy and paste the contents of this model.fit. We still have our early stopping, and now we've added in these dropouts. So both of these things should really help prevent overfitting. We'll go ahead and run this, and we shouldn't expect this to run on all 600 epochs. So go ahead and just wait a little bit, and eventually it should stop running. Notice it did run for a little bit longer, and that's actually good because it means it's still learning even on those further epochs. And that's due to the fact of these dropout layers. So let's go ahead and analyze now these losses here. We'll say model loss is equal to PD data frame, model history, and then we'll go ahead and plot this out. And this is even better behavior. In fact, this is absolutely fantastic. Note that the training loss and the validation loss are both quickly going down, and they essentially are flattening out at the same rate. This is exactly the kind of behavior we want to see. This is much improved over what we saw earlier. Recall our original plot here, where even at that set of epochs, we were already clearly overfitting. So note, adding in the early stopping and adding in those dropout layers has significantly increased performance. So let's do now a full evaluation on our classes. So recall that we're performing a classification task. So we're predicting essentially either a 0 or a 1. And the way this works with Keras is instead of saying model.predict, we actually now say model predict underscore classes. We pass in our test data set, and it will end up showing you the classes it predicts for the X test dataset. And recall that even if you had some new tumor with all these features, it still just predict classes. A new data point is essentially the exact same thing as a test set. So then we'll go ahead and say these are our predictions. And now let's go ahead and say from sklearn.metrics import, and there's two main things we import for a classification problem, and that is a classification report and a confusion matrix. And definitely check out the machine learning theory lectures if you have any questions on things like accuracy, precision, recall, or F1 score. We've actually already covered what those represent. So we'll go ahead and print out our classification report, and this takes in y true. In that case, that's y test, and we directly compare it against predictions. So go ahead and run that, and we can see the results here. So notice we're getting very good performance, and we can check the performance by printing out our confusion matrix, showing the comparison of y test versus our predictions. And that essentially shows that our network only misclassified 1 point in our test set. Yours may be slightly different. You may misclassify a few more specific sets, especially if you're using a different random split than us. But overall, you should have gotten better than 0.95 performance on precision and recall. Okay, so you can also then check out the accuracy here. We're 99% accuracy, and we're doing fantastic on precision and recall. And recall that here that accuracy is a good metric because we saw that we had relatively balanced classes. They weren't perfectly balanced, but they weren't extremely unbalanced either. And that's what this count plot of the actual label was for. All right, so now we have more tools in our arsenal for deep learning. We've understood now that we can add in dropout layers, and we can also use early stopping to not have to worry about the number of epochs that we're training for. So lots and lots of different things that we're going to keep adding to our toolkit to become better practitioners of deep learning with TensorFlow. Okay, thanks, and I'll see you at the next lecture.